Hello and welcome to another lecture on basic electrical engineering paper code ESEE 101. Myself Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today my topic is an overview on transformer. Lesson objective. After the end of this topic, students will able to understand the different types and working principle of a transformer. So, according to William Stanley Jr., transformers are the heart of alternating current system. Overview. Need of transformer. Introduction. Principle. Construction and working, types of transformer and application, the content. So need of transformer. Before approaching to the need of transformer, we have to know what is transformer. So transformer is a static electrical device. The name suggests transformer means it transforms something. So transformer is a static electrical device that transforms electromagnetic energy from one winding to another, which are physically and electrically isolated but magnetically coupled. By stepping up or stepping down the voltage, keeping the power and the frequency constant. So the transformer is a static electrical device which is generally used to stepping up or stepping down. That is called the transformation of the voltage by keeping the power and frequency constant. And they are magnetically coupled but physically isolated windings. So, in most cases, appliances are manufactured to work under some specific voltages. Transformers are used to adjust the voltage to a proper level. The transformers are the basic components for the transmission of electricity. Transformer is used to increase the voltage at the power generating station, that is called the step up, and used to decrease the voltage, that is called the step down, for household purpose. By increasing the voltage, the loss of the electricity in the transmission purpose is minimized. So the introduction part is that I have already told transformer is a static device. It transfers electric energy from one part of the electric or electronic circuit to the another part of the circuit without changing the frequency and also the power rating. That is why I have told that they are magnetically coupled, but those windings are magnetically coupled, but physically and electrically they are isolated. It works on the Faraday law or electromagnetic mutual induction. So the principle of operation that I have told that it works on the principle of electromagnetic induction or electromagnetic mutual induction. So, what does electromagnetic mutual induction means? That when a current is provided to the primary winding, it behaves as electromagnet due to the EMF is induced in the secondary winding as it comes in the area having magnetic field lines due to the primary line winding. So the voltage Vs, that's called the secondary winding voltage, is Ns into ddt of phi. Vs is the secondary winding voltage and Ns is the secondary winding trans. So later this is a coil 1 and this is a coil 2. So it is a current which is provided to a coil 1 which in trans generate a flux magnetic lines of forces. And this is the mutual induction from the coil 1 to coil 2. A coil which is supplied to a current causing a flux to generate, and this flux is mutually inducted to the coil 2. And there is a rate of change in flux with respect to the time according to the Faraday's law of electromagnetic induction, which in turn generate a voltage. So the voltage is directly proportional to the d phi by dt that is known to us for the Faraday's law of electromagnetic induction. So the equation of the Vs is Vs equal to Ns into d phi by dt. So Ns is the secondary winding trans. So this is generally known as electromagnetic induction because EMF is induced in the secondary winding when it's come under the area of these lines of forces, which is created by the primary winding when a current is flowing to the coil of the primary winding. In a simple word, that the current is flowing to the primary winding, it creates a magnetic lines of force, and when this coil is come under these magnetic lines of force, this is called the mutual induction. There is a rate of change in flux with respect to the time, which cause a voltage to develop in the secondary, and uh, according to the Faraday's law of electromagnetic induction, and uh, uh, this is called the electromagnetic mutual induction. And the working principle of the transformer is the electromagnetic mutual induction. So the construction of a transformer having a laminated core. The cores are designed not to have current in it, but still there is a leakage current or the eddy current that is present in the core. So to minimize this current, the cores are laminated. The cores are laminated in order to minimize the effect of eddy current, small amount of leakage current or the eddy current which is present in the core in order to minimize the effect of that cores are laminated. Winding. The windings are made of copper or aluminum coated with very thin layer of isolation. So the general windings are generally made up with copper and the aluminum coated with very thin layer of isolation. Tank. The main function of the conservator tank of a transformer is to provide adequate space for expansion of oil inside the transformer. It is usually cylindrical or cubical. So the tanks are generally used to provide the space for the expansion of the oil. When the transformer is heated up, the oil gets expanded and they are feed back to they are moved to the tank. When the oil get cooled down and they are again come back to the tank. So in these purposes, the cylindrical or the cubical tanks are provided on the transformer. So another is the isolation. It is provided by using synthetic oil between core and the tank. That I have already told that the oil is provided in the transformer. It's the synthetic oil which is normally used as an isolation uh, between the core and the tank of the transformer. And the breather, when the temperature change occurs in the transformer insulating oil, the oil expanded or contracts, and there an exchange of air also occurs within the transformer is fully loaded. When the transformer gets cooled, the oil level goes down and the air gets absorbed within. So when the temperature of the transformer is generally rise up, The insulating oil that I have told that the isolation purpose those synthetic oils are used, the oil expand or contracts and when an exchange of air occurs with the transformer is fully loaded, there's exchange of air. So means that when the transformer gets cooled, the oil level goes down, so the air gets absorbed within it. So this is called the breather. So this is the general construction of a transformer where the laminated O is there, winding tank isolation, and the breather is there in the transformer. So this is the construction of the transformers. The core are there for in order to minimize the leakage current or the eddy current. Windings are generally made of copper or aluminum, and the cores are laminated. Windings are made of copper and aluminum coated with very thin layer of insulation. Tank are generally in the form of cylindrical or cubical tank that is provided in the adequate space for the expansion of oil in the transformers. The isolation are synthetic oil, which is generally used as an isolation purpose between the core and the tank, and the breather is there. Breather is generally there in order to so that the temperature when it changes, but there the exchange of the air also occurs within the transformer when it is fully loaded, and when this oil gets expanded, and when the transformer gets cooled down, the oil goes down, and the air absorbed within it. So this is the general construction of a transformer. So the type of transformer. So transformer can be divided on the basis of construction, on the basis of winding, and the basis of coolant metal use. So the basis of construction transformer are divided into three categories. One is called the core type transformer, shell type transformer, spiral core transformer. Basis on the winding, transformer are classified into step up transformer, step down transformer, isolation transformer, and the basis of coolant material use. Transformer are classified into oil-filled self-cooling, oil-filled water cooling, and the air blast. So transformer are classified on the basis of construction, basis of winding, and the basis of coolant material use. And now they are also subdivided into the basis of construction purpose. In case the basis of construction, code type, shell type, and spiral code type transformer. Basis of winding, step up, step down, and isolation transformer. Basis of coolant material use, oil filled self cooling, oil filled water cooling, and the air blast transformer. So now we are discussing about the basics of construction. The first is the core type transformer, and its core has two limbs. The windings are wounded on two limbs of the core material. This is the core type transformer, and this is the two limbs, and the windings are wounded on the core type transformer. So this is one of the core type transformer that we have seen. The core has two limbs and the windings are wounded on two limbs of the core material. Shell type transformer. The core has three limbs and two windows. Both the windings are wounded on the central limbs, one over the other. So this is the shell type transformer where there is a single there is a core has three limbs and the two windows, and the both windings are now wounded on the central limb. That is that we have seen. The windings are wounded on the central limb. This is a cell type transformer. Spiral core transformer. The core constructed is similar to the wheels of spokes. The wheels of the spoke that we have seen, the core is constructed in that way. Uh, the windings are wounded the spokes like a structure. So this is a general spiral core transformer where the constructor are similar to the wheels of a spokes. So the windings are wounded on the spokes like a structure. So this is called the spinal cord transformer. So basis of the windings, the step-up transformer. The number of windings on the primary side is less than the number of windings on the secondary side. So here that is called the step up means the primary side has say 120 windings and the secondary side has 240 windings. It is or in other words, you say the primary voltage is 110 by 120 and the secondary voltage is 220 by 240. So it is generally seen that the ratio is 1 is to 2. So the secondary voltage is more compared to the primary one. So this is called the step up transformer, or in other words, the NP, the number of turns in the primary side, is less than the number of turns in the secondary side, NS. Step down transformer, the number of windings on the primary side are more than the number of windings on the secondary side. But the NP, the number of windings on the primary side, is greater than NS, the number of windings in the secondary side. So it is primary side coil is saying that the voltage is 220 by 240 and the secondary is 110 by 120 volts. So it is obviously the primary having a more number of turns and ratio is 2 is to 1, and secondary having a less number of turns. So it is called the step down transformer. So the another is the isolation transformer. The number of windings on the primary sides are equal to the number of windings on the secondary side. NP equal to NS. So it is the number of turns in the primary side and number of turns in the secondary side that's equal. So this is known as isolation transformer. So basis of the winding transformers are divided into step-up transformer, where the NP, the number of turns in the primary side, is less than the NS, number of turns in the secondary side. This is called the step up transformer, step down transformer, where the NP greater than the NS, that is the number of turn of the primary side, is greater than the number of turns in the secondary side, and the isolation transformer where NP equal to NS, that is the number of turns in the primary side equal to number of turns in the secondary side. So in this way, the step up transformer, step down transformer, and the isolation transformer are designed. Yes, the basis of the coolant. So one is called the oil-filled self-cooling. So oil-filled self-cooled drives are used small and medium-sized distribution transformer. The assembled windings and the core of such transformers are mounted in a welded, oil-tight steel tank provided with a steel cover. The oil helps in transferring the heat from the core and the windings to the case from where it is radiated out to the surrounding. The oil filter and it is cooled by the self one. When that oil gets expanded and it is moved up to the breather, and then when the air is come from the outside and it absorbs the air within it and it gets cooled down and come back to the tank. And this is the general oil filtered self cooling transformer. Oil filled water cooling, this type of is used for much more economic construction of larger transformer. The cooling coil is mounted near the surface of the oil, though which is though the which cold water keeps circulating, and this water carries the heat from the device. This is the oil filled water cooled, but the water is generally circulating in nature and it carries the heat from the device. Air blast is the air blast transformer, and this type is used for the transformer that use voltages below 25,000 volts, 25,000 volts. The transformer is used at house. So this is on the coolant, that is the oil filled self cooling, oil filled water cooled, and the air blast. The air blast, this type of transformer that is used voltages below 25,000 volts. The transformer is used at houses. So now we are concentrating on the ideal transformer. So ideal transformer, the definition of the ideal transformer is that an ideal transformer is an imaginary transformer which does not have any loss in it. Means no core loss, copper loss, and any other losses in the transformer. Efficiency of this transformer is considered as 1000%. Means there is no loss associated with that transformer. There is no coal loss, there is no copper loss, or there is no any other losses in the transformer. So efficiency of this transformer is considered as 100%. This is known as ideal transformer. So ideal transformer model. The ideal transformer model is developed by considering the windings of the transformer are purely inductive. So we are considering the transformer windings are purely inductive and the core of the transformer is loss free. Also, there is zero leakage reactance of the transformer. Reactance is the opposition to the flow of current from the electric element due to its inductance and capacitance. So we are considering that the model of an ideal transformer where develop where the windings are purely inductive in nature and the core of the transformer is lossless. Also, there is a no zero leakage reactance of the transformer. Reactance is the opposition. What is reactance? Is the opposition to the flow of current from the circuit element due to its inductance and capacitance. That means 100% flux passes through the core and links with both the primary and the secondary windings of transformer. Although every winding must have some inherent resistance in it which causes voltage drops and I square R loss in it. In such ideal transformer model, the windings are considered as ideal, that is fully inductive. That means resistance of the winding is zero. So we are considering the windings are fully inductive in nature, means there is no resistance. The resistance of the winding is zero. The leakage reactance of the transformer is zero, and the core of the transformer is generally lossless, no loss or loss free, which is called the ideal transformer model. So, if an alternating voltage V1 is applied in the primary winding of an ideal transformer, so this is the ideal transformer. So, if an alternating voltage V1 is applied the primary winding of the transformer, and it will induce a voltage E1 in the primary. Uh, uh, that is what the main purpose. The purpose is that if a current, if alternating voltage will apply, it will cause a current to flow, and this current in flowing through the winding cause a flux to generate, and this flux is the core of the transformer, and this flux that is rooted in this part, in the core, and this flux is also there in the secondary portion. So this is the general conception of the mutual inductance that we have told, that the flux is rooted and mutually inducted. Okay, and for that V1 purpose, a voltage E1 also be induced because there is a rate of change in flux with respect to the time, and also an E2 voltage will be induced when it is closed circuited. Means there is a rate of change of flux with respect to the time. So this is called the mutual inductance, and the main flux in the core remain same. And this is routed through in this path. This is the core path, and the alternating voltage V1 is applied. It is the primary winding, or say the primary winding, or it is the secondary winding. And depending upon the number of turns, we can say this is a high voltage winding, and it is the low voltage winding. And it is clearly seen that the number of turns are different. So it is a general, here the number of turns is less and here the number of turns is more. And if I take connected a load here, so it is act as a step up transformer. So, a alternating voltage source V1 is applied in the primary winding of the ideal transformer. There will be a counter self EMF V1 that we have already seen induced in the primary winding, which is purely 180-degree opposite, and the phasor opposition with the supply voltage. If this is a supply voltage, the counter EMF will be 180-degree opposite to the supply voltage, and it is clearly seen in this figure. This is called the counter EMF E1. Now, for developing counter EMF E1 across the primary winding, it draws current from the source to produce required magnetic flux that we have already discussed. And this flux is routed through this core and cause a mutual inductance between the primary and the secondary winding. And as the required magnetic flux. As the primary winding is purely inductive, the currents lag 90-degree from the supply voltage. It is clear that the primary winding is purely inductive in nature. So the current will, because we are considering the ideal transformer, so the current will lag by an angle 90-degree from the supply voltage. It is the supply voltage V1 and current is lagging by a 9 angle 90 degree. And this current is generally responsible for producing the flux. This current is called the magnetizing current of the transformer I0. Transformer, transformer, and it is represented by I mu. The magnetizing current is represented by I mu. This is called the magnetizing current of the transformer. It is clear that this is our V1, the voltage, applied voltage. This is our E1, the counter EMF on the primary side, or the primary winding, and the flux that is generated is routed through the core, This flux, as this is the purely inductive in nature, so flux current, as the voltage is applied, a current will flow, and this current, which is responsible for producing the flux, being a purely inductive primary winding, it will lag the voltage by an angle 90 degree. It is clearly seen in the phasor diagram, and this flux, this current is generally known as magnetizing current of the transformer, and it is the symbol is I mu. Now, this alternating magnetizing current I mu produce an alternating magnetizing flux that we have already discussed. The flux is proportional to that current which producing it, hence the flux would be would be in phase with the current. That we have already known that this current I mu is generally responsible for producing the flux. So flux will be proportional. How much flux will be produced? It is proportional to the current. So means that the flux will be in phase producing. So flux will be in phase with the current. Flux also links the secondary winding through the core of the transformer. As a result, there will be another EMF E2 will be induced across the secondary winding, and it is mutually induced EMF as shown in the figure below. That is the E2. At no load, it equal to V2. That is the E2. At no load, it equal to V2. So when this flux is, so what the basic that we have learned, that a voltage that is applied to the primary side, and it will allow a current to flow through this coil, and when a current is flowing through a coil, also the inductive coil, it will produce a flux phi proportional to I, and phi equal to Li, and this flux will rotate through the core and create a mutual inductance between the secondary winding, and when a flux is flowing through that secondary winding, there will be rate of change in flux with respect to the current, and it will induce a voltage E2 in the secondary winding. Same, this is called the counter EMF. And same in case of the E1, a voltage will be induced, and which is 180 degree opposed to the voltage, applied voltage V1, and the current which is responsible for producing the flux, which is known as I mu, the magnetizing current of the transformer, and as it is flowing through the coil or the purely inductive winding, so it will be lagged the voltage by an angle 90 degree, and the flux which is generally directly proportional to the current flowing through the coil, and this flux is always in phase with the I mu. And which is seen, those two things are seen in the two phasor diagram representation, two diagram, which generally shows in the figure that is below. So the ideal transformer, if I whatever we have learned, that we summarizing, so we just summarize those things. We will learn that the no winding resistance is there, no leakage flux, that is the same flux links both the windings, no iron losses, that is eddy current and the hysteresis losses in the core, that we have seen that the same flux is linked between the two windings, so there is no leakage flux, no winding resistance, no iron losses, that is eddy current and the hysteresis losses in the core. So from the view of the conception of the ideal transformer, the another uh, conception is arrived at the practical transformer. A practical transformer differs from the ideal transformer in many respects. The practical transformer has the iron losses, the winding resistances, magnetic leakage gives rise to the leakage reactance. So the practical transformer have the iron losses, the winding resistance, and the magnetic leakage that giving rise to a leakage reactance. So the iron losses. Since the iron core is subjected to an alternating flux, there occurs a eddy current and the hysteresis loss in it. These two losses together are known as iron losses or the core losses, the eddy current loss and the hysteresis loss. The iron losses depend upon the supply frequency, the maximum flux density in the core, volume of the core, etc. It may be noted that the magnitude of the iron loss is quite small in technical transformer. So the hysteresis and the eddy current losses are generally known as the iron loss, the hysteresis and the eddy current losses. So the winding resistance. Since the winding consists of copper conductors, it immediately follows that both primary and the secondary will have winding resistance. The primary and the secondary. The primary resistance R1 and the secondary resistance R2 act in series with the respective winding as shown in the figure. This is the R1 primary and this is the R2 the secondary resistance. When the current flows through the windings, there will be power loss as well as a loss in voltage due to the IR drop, I square R loss. Voltage drop is due to the V equal to IR and the losses I square R losses will be there or voltage. This will affect the power factor and the E1 will be less than the V1 and V2 will be less than E2. So this will affect the power factor and the E1 that is the induced voltage must be less than the V1 and while V2 will be less than the E2 because there is a voltage drop in this primary side and in the secondary side also. So the leakage reactance. Both primary and secondary current that is produce the flux. The primary current produce the flux, the secondary current produce the flux. The flux phi, which links both the windings and whose flux is called the mutual flux. That I have already told that the flux which is generally link the primary and the secondary winding, generally links the primary and the secondary winding is known as mutual flux. However, the primary current would produce some flux phi, which would not link the secondary winding. Similarly, the secondary current produce some flux phi, which would not link the primary winding. So, some amount of flux which is produced by the secondary winding and also the primary winding. So, this is not linked with the secondary winding. It is clearly seen in the figure that this flux, it is called the main flux or the mutual flux, or the useful flux is linked between the two windings, but some portion of the flux that is generated in the primary and the secondary winding, it is not linked with each other. So this flux, that is phi 1 and phi 2, which are links only the winding, is called the leakage flux. The leakage flux paths are mainly through the air. The air is the main path for the leakage flux. This is called the leakage flux. The effect of this leakage flux would be the same as though inductive reactants were connected in series with each winding of the transformer that had no leakage flux as shown in the figure. In other words, the effect of the primary leakage flux phi 1 is to introduce an inductive reactant X1 in series with the primary winding as shown. Similarly, the secondary leakage flux phi 2 introduce an inductive reactant X2 in series with the secondary winding as shown. This one, X1 and the X2. This one is the X1 and the X2. Okay. So this is called the for primary leakage flux phi 1 there is an inductive reactance X1 and the secondary leakage flux phi 2 inductive reactance X2. There will be no power loss due to the leakage reactance. However, the presence of the leakage reactance in the winding changes the power factor as well as there is a voltage loss due to the IS drop. So voltage drop due to the IS drop will cause change in the power factor. So this is called the leakage reactance. The main flux or the mutual flux or the useful flux that is the flux that is linked the both windings, this one, and a flux, the path of the flux is the air. This is going within the core, the main flux of the useful flux, and the flux which are generated by the both two windings. This is called the leakage flux, and these flux are paths are mainly um, through the air. This is called the leakage flux. And due to the leakage flux, a voltage drop Ix will be occurred, and it will affect the power factor. Windings, it changes the power factor. So, although the leakage flux in the transformer is quite small, it is 5% of the main flux phi compared to the mutual flux phi, it is a 5%. So, but we cannot ignore it. It is because the leakage flux are, although the air of high reluctance, the flux path that we have already discussed of the leakage are the high reluctant air path. The air path, the flux path of high reluctant and hence require considerable EMF. It may be noted that the energy is conveyed from the primary winding to the secondary winding by mutual flux, which links the both the windings. So, though the leakage flux is about the 5% of the uh, main flux, the mutual flux, but the leakage flux, the path for the leakage flux is the air which having of high reluctance. So, we have to keep in consider the conception of the leakage flux. So, the application, the transformer, the transmitting electrical energy over large distance through wires. Transformer with several secondaries are used in television and radio service receivers where the several different voltage are required. Use as voltage regulator used almost everywhere in day-to-day life. So today we have learned about the transformer, the working principle of transformer, different types of transformer, and the application of the transformer, and along with the conception of ideal and the practical transformers. Thank you.